Chemistry. Yay. All right, so this is where we left off on a week ago, last Monday. This is where we were last Monday. So in yeast, alcohol dehydrogenase reduces acetaldehyde to ethanol. So we know the two half reactions that we need is going to be the acetaldehyde making ethanol. And this reaction, this alcohol dehydrogenase, we know uses NAD plus and NADH. So the question is, based on the wording of the question, right, these are both written as reductions from our table of reductions. Based on the written portion of the question, which one of these reactions should stay as a reduction reaction? The first one or the second one? The first one. So this one is our reduction reaction. So then what does that make the second reaction? The oxidation reaction.
Wait, why is it that reduction?
Because the wording of the question says we reduce acetaldehyde ethanol. So, do I need to change the sign and or value of this E0? No, cardinal sin, don't touch it.
Would it come up with a different
What they do is they reverse it and then they add it. I leave it alone and just subtract. I think that's easier because there's like one less step to mess up. If you can identify which one's the reduction reaction, the other one's the oxidation, then you subtract reduction minus oxidation. Always. Always. You can do it the way the book does it, where they choose to flip over this and then change the sign and then add it. That is fine too. But this is the way I teach it in, this is the way most people teach it in Gen Chem. Just trying to stick with the same method. All right, so if I do that subtraction, it's a positive delta E, so is that spontaneous or non-spontaneous? Spontaneous, yeah. So then the question wants me to find delta G. So to find delta G, I use the equation negative NFE. What value do I put in for N? N is the number of electrons being transferred. 2. Mm-hmm. If you get a negative delta G, what is that, spontaneous or non-spontaneous? Good, which matches up with what we said one line earlier. Achoo. All right, questions on how to do that math. Pretty straightforward. All right, so then the question is, how does this apply to the electron transport chain? So again, these figures come from your textbook. That's not terrible. Okay, the sequence of electron transport is the oxidation of NADH and FADH2 carried throughout the 4 parts of the electron transport chain. And we're going to use a set of protein complexes that each contain redox centers to help with the oxidation and reduction of these NADH and FADH2s. Okay, and as a rule, electron transfer goes from low to high potential values. So as we're looking at, I'll zoom in a little bit on my picture over here. So here's the electron transport chain. Here is my value of standard state reduction potentials on the side. Complex 1 oxidizes NADH to NAD plus with 2 electrons. That potential is negative 0.315. Once we get through complex 1 to complex 3, so you can either go 1, 3, 4, or you can go 2, 3, 4. That's the order of the complexes. You can either go 1, 3, 4, or you can enter from 2, 3, 4. So 2 different ways through the path. So I'm going to look at 1 to 3 to 4 first. So the oxidation of NADH to NAD plus is negative 0.315. To go to complex 3 is at plus 0.235 volts. And so we've gone from a negative value to a positive value. So the electrons are going low to high. Then if I go from complex 3 to complex 4, I'm going from plus 0.2 to plus 0.8. So again, I've gone from a lower value to a higher value. So the electrons are going this way. Or we can enter in from the citric acid cycle. So complex 2 is succinate dehydrogenase. So it's a membrane-bound protein, which is where the citric acid cycle interlocks with the electron transport chain. It's called complex 2 in this system. So we're going to oxidize FADH2 to FAD, transfer those 2 electrons from Q to CoQ. So it's really a 2-step electron transfer. But that has a value of plus 0.045. And then again, it goes up to 0.2 and then 0.8. So again, going low to high values. Yeah?
The values like next to the cytochrome and the CoQ,
Yep.
are those the delta or the
Those are just E-naughts.
for all of them?
The deltas are here in the middle of the box.
Okay.
And so those are the difference between here to here, here to here, here to there. So in the little box, there's a delta E0, and then they've also calculated out the delta G for you for each step. As you can see, some of these delta Gs are fairly negative, right? Negative 112 kilojoules, which means this is a very spontaneous step going in that direction. And then the final step is we're going to make water. So and to provide energy to make ATP. So the electron transport chain does not directly make ATP, but provides the energy to do it in the next step. All right, so let's take a look at each one of these complexes and how they work. All right, so complex 1, and again, all these figures are in your textbook. Complex 1 passes electrons from NADH to CoQ. So CoQ contains one molecule of flavonomononucleotide. What's the other molecule we know that contains a molecule of flavonomononucleotide? Right, FAD, right? So CoQ is very similar in function to FAD. They just have a different thing surrounding it. CoQ also contains what are called iron-sulfur clusters. So here's my figure. It's a little hard to see. Let's see if I zoom in a little bit. There we go. NADH plus a proton is going to transfer 2 electrons through complex 1 to Q, changing to QH2, which is just like FAD, right? FAD goes from FAD to FADH2. So they operate very similarly.
Can you slide the page over?
Yep. Yep. All right, so complex 1 contains these iron-sulfur clusters, and they form like a chain along this path. So that the electrons are really transferred from the NAD to an iron-sulfur to an iron-sulfur to an iron-sulfur to finally get out here to find the CoQ molecule. So a free electron can actually travel in space all by itself, about 14 angstroms, which is actually pretty far. It can leave, it can jump off a molecule, travel by itself through space, 14 angstroms, to find the next center. So these centers don't have to be covalently linked. They don't have to be even all that close in terms of molecule space to get from one to the next one. Let's see what else. Q, just like FAD, in the end accepts 2 electrons, but it accepts them one at a time. So it doesn't take both electrons at once. It goes Q to QH, QH to QH2. And the final step it needs to do is it needs to pump 4 protons into the inner membrane space from the matrix. So we're going to build up a concentration gradient across the membrane that we're then going to use when we make some ATP. Okay. So let's take a look then at complex 2. The other way the electrons can enter into the electron transport chain is through our succinate dehydrogenase, right, from our citric acid cycle. So succinate dehydrogenase, which is our 6th step of the citric acid cycle, is actually embedded in the inner membrane of the mitochondria and passes electrons from the reduction of succinate to CoQ. So complex 2 contains 3 iron sulfur centers and a molecule of cytochrome C. So complex 2 does not pump protons, unlike some of the other complexes, but its job is to provide more electrons to the system to do more reductions.
You mean direct protons instead of electrons?
Oh, yeah, that should be H+. Sorry, pump protons. It doesn't pump electrons either. That'd also be true, but none of them do, so. All right, so, right, we don't go complex 1 to complex 2, we go 1 to 3 or 2 to 3. And so at the end of complex 1, right, we had made a QH2, and at the end of complex 2, we've made a QH2. So these QH2s they're a collection point for electrons. So if we look at kind of this scheme, right, complex 1, it's showing 1, 3, 4, but 2 is in this area. This Q that's in between 1 and 3 is also in between 2 and 3. So it's the same Q, it's just either collecting electrons from 1 or collecting electrons from 2. Right, same thing here in this chart. Either I go complex 1 to CoQ or complex 2 to CoQ, and then 3, 4. So it's a collection point for electrons. So complex 3 is going to take all those electrons that have been collected in the form of QH2 and convert them back to Q so that they can go through the cycle again. So complex 3's job is to pass electrons from these QH2s into a cytochrome C, which is shown down here at the bottom. So it's going to oxidize QH2 back to Q, pass those electrons down to cytochrome C, and regenerate the original Q so that it can receive more electrons from complex 1 or 2. So cytochrome C, I'm sure you've talked about in a billion other classes, but just in case you haven't, what does this look like, this middle part? The iron stuck to 4 nitrogens. It is a heme group, right? It looks just like the same one in hemoglobin. It is. So cytochrome C is a protein that contains a heme group. And that center iron can accept electrons to form iron plus 2 and then regenerate back. All right, so it can go 3 to 2, 2 to 3, either way. So unlike when you have your hemoglobin, you don't want extra electrons in there, right, because you want the oxygen to be able to latch in and not become oxidized and reduced. Here, we're choosing to oxidize and reduce it to send electrons someplace else. All right, so now we've passed our electron. Oh, last thing. We're going to pump 4 protons into the inner membrane space. So complex 1 does 4 protons, complex 3 does 4 protons. Okay, so now complex 4, oh, sorry, let me talk about the Q cycle first, because we just finished the Q cycle. So the Q cycle is looking at this Q molecule right here between complex 1 and 3 or 2 and 3, this Q. That is not very in focus, sorry guys. Again, this is in your textbook, so don't feel like you have to copy it all down. So the Q cycle is regenerating that co-Q between the 2 complexes, either 1 and 3 or 2 and 3. And so in the first round, we have QH2 that we just made with complex 1 or 2. It's going to donate 1 electron to a cytochrome, to an iron sulfur, which then going to transfer to a cytochrome and transfers to a cytochrome. Its second electron is going to transfer to the cytochrome up here. Right, so CoQ, or QH2, so I had this written before, but this will help clear it up. Right, we're going to transfer 2 electrons overall, but it chooses to do it 1 at a time. So it's going to transfer 1 electron down this way, and then 1 electron up here, to make this semiquinone, this Q minus. And then another QH2 is going to enter, transfer 1 electron down here to the cytochrome, transfer 1 electron up here to remake that QH2. So it chooses, instead of passing both this way, it splits them. It goes 1 up, 1 down, and a second round, 1 up, 1 down. So in the end, the net result is we're going to pass 2 electrons, well, 4 electrons from 2 QH2 molecules. So we're going to pass 4 electrons from 2 QH2 molecules. In the end, we reduce 2 cytochrome Cs. We make 1 Q molecule. And we're going to pump 4 protons. You guys don't look as excited as you should be about doing the Q cycle.
I was only 1 QC.
Why only 1?
Well, yeah.
Because the first time we make this semiquinone, and the second time we finish making it into QH2. Oh, I guess QH2. We do make these 2 Qs. I guess I could.
Q's are regenerated.
Yeah, 2 Qs are regenerated and we make 1 QH2.
Okay.
Yeah. So by transferring these electrons from here, we get 2 Qs back and we make 1 new QH2. All right, so we did this twice to make 2 Qs. We did that to make 1 QH2, and then we make 2 of these.
Where are those two other hydrogens come from? That go in
The 2 other what?
the hydrogens up top that come in.
Oh, where do they come from?
Yeah,
Space. Yeah, floating around.
I don't know.
No, they just come from other things going on. So now we're ready to take those electrons, send them off to complex 4. We're getting real close to the big finale. Complex 4 catalyzes 1 electron oxidation of 4 consecutive cytochrome C molecules. So what's going on here is we have 4. All right, we're going to take 4 cytochrome Cs in the iron plus 2 state. Oxidize them to iron plus 3 and reduce oxygen to water. So I've gone from iron plus 2 to plus 3, so that's an oxidation. And the water has gone from an oxidation state of 0 to minus 2. So it has gotten reduced. So it's going to require 4 protons from the matrix, right, to make our 2 water molecules. So we're going to need 4 protons. But But doing this reaction will also pump 4 protons. So it's going to use 4 protons and pump 4 protons. It's going to move 8 altogether. So this, for whatever reason, the textbook decided to do it a half of what it is. Instead of doing a whole oxygen, it's half an oxygen, making 1 water. So just double everything in the picture to get to 2 waters, 4 protons, 4 protons. So we have now made our final product, which was water. We've pumped a bunch of protons across the membrane. So now we're going to harness that energy that we've made to make some ATP. So, oxidative phosphorylation. All right, so we're going to go through an endergonic process to make an ATP from an ADP and a PI. Oh, there we go. So the energy needed to do this reaction is conserved by pumping all those protons from the matrix to the inner membrane space. So this proton gradient is the only reason this ATP synthesis is possible. All right, so let's take a look at some of the things that have to come into play for oxidative phosphorylation to occur. First one should be a gimme. In order to do this, right, you have to have an intact membrane. Can't have a membrane with holes in it. Why do we need to have that membrane impermeable to other small charged molecules? Right. It would affect the charge, right? If we were able to freely pass other charged molecules across the membrane, we wouldn't have a gradient anymore. So we're going to pump the protons out of the matrix into the inner membrane space, which means this inner membrane space, just like in the picture, has a high proton concentration. So complex 5, which is our ATP synthase, as part of its making the ATP, is going to pump the protons back to the matrix. So we do have a cycle. We're going to push them all into the inner membrane space, but we do have to have a way to get them back into the matrix. Yeah, I guess those are the big 4 points. Does the inner membrane space of the matrix have a higher pH? Higher is in closer to 14. Okay, right. High proton concentration, is that more acidic or more basic? So if it's more acidic, does it have a high pH or low pH? Low pH. Mm-hmm. This pumping protons into the inner membrane space, that's going to take work, right? Because you're pumping into a spot that already has a lot of protons. So then pumping them back out with the gradient is going to provide that energy to make the ATP. So pumping those protons back from high to low, going with the gradient, is going to provide the energy to work our ATP synthase mechanism. Okay. We'll at least get started on ATP synthase. We will finish this Wednesday. I have a little worksheet for us to work through on Wednesday, and then a quiz, then you can turn to some questions. So I'll start ATP synthase, but I won't have enough time to finish it. All right, ATP synthase, which is sometimes referred to as complex 5. Sure. Your quiz. I mean, it's going to be a quiz. So it can be a group quiz. Sure, sure. All right, complex 5, ATP synthase, is a multi-subunit enzyme. And it also is a binding change mechanism. So let's work through each one of these points first. So it's 2 parts, F0 and F1. F0 is water insoluble, F1 is water soluble. So where would I expect to find F0? In the membrane or in the inner membrane space? Right, water insoluble, we are going to find that in the membrane. We're going to find F1 with its head poking out into the matrix. All right, so binding change mechanism means that as something binds to the enzyme, it's going to physically change its shape to change where the active site is, or change the shape of the active site. So here's my fancy little schematic. We'll work through what all these letters mean here in a second. But we can think about it as tight, open, and loose. So ATP is going to be bound in a tight active site. I'll then add ATP and a PI into the loose active site, which has some flexibility in it. I will add some energy. And you can see my letters have changed. It used to be L, T, O. Now it's T, O, L. So tight is now with my ADP and PI. My open is for ATP. The ATP can now float away. In the presence of a little bit of water and a few other things, I'll now tighten down the active site, make ATP, and have my two sites open again. So physically, the active site is changing shape. And I'll have a video on Wednesday. It's a little easier to see in a video form than it is on this. But the actual top of the enzyme is actually spinning around and changing the shape of the active site, squishing them together, opening them up. It's a pretty neat little enzyme.
So after step 2, like when you release ATP,
Mm-hmm.
and it comes back? And,
Oh no, this is now this.
oh, okay.
Yep, in the tight binding site, I had ADP, PI. I've now squished them together to make ATP. And this one's floated off. This one's this one. So let me walk through in words, and I'll spend some more time on this on Wednesday. So we're pumping protons using our F0 in the membrane part of the protein. We're going to be making the phosphate anhydride bond to make the ATP using F1. And then we are going to couple the action of F0 and F1 to change the proton gradient in that zone. All right, we will finish this chapter Wednesday. We'll have a little quiz over 15 stuff. So there's only, one slide left or so. Then you'll turn in questions for Friday, review day. Maybe I'll see some of you guys at the EBS seminar this afternoon.